due on Thursday. Reminder. Any questions about it?
The last question.
Huh?
The last question.
Yes.
In the homework.
Yes.
I don't understand
What is being asked?
Yeah.
So basically you're being asked to calculate the effect of the interaction from like minus infinity to plus infinity, right, using the time development operator on the matrix elements, finding the matrix elements, right, from like n to n of the harmonic oscillator, but using the forcing. Is that what you're asking me, or you're saying even?
That's like the end of the third question.
Oh, I'm sorry, then what's the fourth question? I forgot. What was the fourth question?
I don't remember.
Okay, maybe we can, oh, you have it.
Absolute energy difference.
Oh, yes, yeah, this is exactly what I was trying to tell you. Right. Okay, well, I mean, the basic idea is that you want to calculate delta E, right? So you start with psi, and you apply a forcing interaction, which is transient. And the question is, what happens to delta E, right, after time infinity? So the way you can think about that is, you take psi at some time infinity, right, and apply the full interaction, which is h, and then find, right, this would be the change in the energy of the system from. And so the question is, you know, what is the state using the time development operator for this system at time infinity? And that will help if you sort of either use the time development operator that I derived in the class. So class notes are available now. So you can actually just use that result for the time development operator and then calculate this forcing, calculate this change for the psi. So you just directly plug it in from that time development operator. It's in there, right? I think in my notes. I don't know if anyone has my notes here. I guess you're being asked to find the change in the energy, so you should take this minus the original energy, which is psi h, psi. Okay. That didn't help? Did that help or did not help?
I think it helped.
Okay. If not, we can talk after class. In the last class, we were looking at the atom field interaction. Specifically, we were trying to show that the correct Hamiltonian for an atom interacting with a field is one that we can rewrite in a gauge transformation. So, to be more, to remind you, we started with this Hamiltonian, which is the full Hamiltonian of an atom in the presence of an electromagnetic field. And the claim was that if we make the correct gauge transformation and approximations, then we can rewrite this Hamiltonian as H prime equal to P E squared over 2 ME minus mu dot E at R equal to 0, T plus V of R. And what were the two assumptions or approximations that I said that we were going to make? Anybody recall from last class? Which approximations will lead us to this result? We were going to carry out the math, but before we do that, it's always important to know your assumptions, because it only works under certain assumptions. Coulomb gauge, very good.
And the potential is not related to the position.
Sorry?
The potential is not related to the position.
Potential is not what?
Not related to the position.
Not related. What does that mean?
I mean, independent.
Independent, very good, yes. So, right, so the assumptions are one, and I think we had a question about whether this is already, let me finish writing it. So the two assumptions are this, we're going to set del dot A equal to 0 and phi equal to 0. And the other is that A at R comma T is approximately the same as A at position 0 comma T, where 0 of course is the position of the atom or the nucleus of the atom. I think somebody had a question that isn't this somehow del dot A equal to 0 already a choice of gauge, right? And so isn't that already like a gauge transformation? And it is true, we are choosing a gauge, but remember in quantum mechanics, any choice or any arbitrary transformation of gauge must be accompanied by a transformation of this wave function with a exponential e to the I kind. So to be more specific, just to answer that earlier question is that for any gauge transformation, which is phi prime equals, say, phi minus d chi over dt, A prime equals A plus rad chi, right? This is any gauge transformation that leaves the electromagnetic field E and B the same, right? Because if you substitute that back into the equations for E and B, that will leave them invariant. But in quantum mechanics, we also need to transform the wave function by this quantity to leave the equations invariant. That is basically to allow the Hamiltonian and everything else to produce the same, effect or energy levels. So we have not yet made that transformation. That's what we are actually doing here on this system. We are making a unitary transformation or gauge transformation that by choosing the Coulomb gauge will then appropriately transform the Hamiltonian to be the one that we are now looking for, which is in terms of these electric field. Does that answer your question? I think it was you who asked me this question, right? Was that kind of what you were getting to?
So I think my original question is whether we are going to apply the Coulomb gauge after the gauge transformation, or we apply the Coulomb gauge and then do the transformation. So I think there is a freedom for gauge choice hidden in this problem.
Okay.
Right. So when we fix the Coulomb gauge, then we are choosing a gauge. So if we
Yes.
have already applied the Coulomb gauge, then
Yes.
we are using the gauge transformation. We transform from Coulomb gauge to some.
Well,
some
at this
other
point, I don't believe I've chosen any gauge.
So if we apply the Coulomb gauge after the transformation,
Right.
then it means we assume that we are.
I mean, we are allowed to make any unitary transformation we want.
Yeah, it's
Call it a unitary transformation or gauge transformation,
Yeah,
whatever you
it's
want to
true.
call it,
yeah, yeah.
right? And then we apply the Coulomb gauge.
Yeah. So what I mean is basically we are choosing some gauge at this point, because this gauge after the transformation, the gauge transformation, it goes to the Coulomb gauge.
Mhm.
That is my understanding. So I just want to make sure my understanding is true.
Okay. I'm not sure. Okay, I'll let you think about that. You're saying even writing down this Hamiltonian is equivalent to choosing a gauge?
No. So
Oh, okay,
what I
sorry.
mean is we have done the transformation till here.
Here?
Only the gauge transformation, but we don't specify a gauge right now.
Oh, well, in the process of going from here to here,
Yes.
which I will now do,
Yes.
I will use the Coulomb gauge. So I will carry out a unitary transformation on the Hamiltonian,
Yes.
and then as I recalculate the Hamiltonian,
Yes.
I will have to apply some gauge for the E,
Yeah.
A and phi.
Exactly. When we
Right.
do the transformation, we didn't specify the gauge.
That's right.
But when we fix the gauge as the Coulomb gauge, then it means.
Then we end up with this Hamiltonian.
Right. Exactly.
Correct.
Yeah. I
Exactly.
think my question is.
That is correct.
somehow answered.
That is correct. Exactly. And if you want to read more about this, it's actually a subtle concept. I mean, theoretical, as you said. It's a very subtle theoretical concept about the order or the exact way in which you apply this. You can go to Scully, section. I mean,
5.9.
I don't think it's very different from what I've said earlier, but he has more detailed discussion about this.
In
Section 5.1
5.8.
and also 5.8. Okay, you have it then. Okay. All right. Yes. Okay. So I am pretty much following what he's saying. So. Okay. So to finish the story, then, so that's the assumptions, and now we have to do the algebra. I won't go through every step in the algebra. I'll ask you to carry some of it out. But so the transformation that, if you recall, the transformation that we are making is e to the minus I q r dot a over h bar. Okay, q is the charge on the electron. So sometimes I put q, sometimes qe. Okay, so to carry out what happens, and remember I told you that under this unitary transformation, because the unitary transformation has a time dependence, right? A is not time independent. It has, even with approximation that r can be written down as 0, there's still time dependence, which means that when we carry out the unitary transformation, we have to keep track of that, or we have to be careful about that, and the actual Hamiltonian, or the transformed Hamiltonian, will be like this. Okay? So this will be the new Hamiltonian after the transformation. So first then, let's write out h, which is 1 over 2m p minus qa whole squared plus q phi plus v. And now I'm skipping writing r, t, all that stuff. Basically it's all assumed, which of course if I expand this guy, there are two terms, or four terms. And initially I have to be careful because A is dependent on R and T at first, right? So at this step, I have not yet made the approximation. So we have to worry about P acting on A or A acting on P. And then of course there's the Q squared A squared term. And then still the Q phi plus. And in the dipole approximation, since this is called the dipole approximation because I kind of mentioned to you in the last class that we are assuming that the wavelength of the variations in the A, so if you Fourier expand A, for example, then it will have some wavelengths of variation, K. And those wavelengths we are assuming are all much larger than the size of the atom, and therefore we can purely worry about only the atom's dipole moment. And if you want to look at the higher order moments, you can, but we are ignoring that in this approximation. Okay. So in the dipole approximation, A at R T is equal to is approximately A at 0 comma T, which means that this A over here, A dot P and P dot A can be interchanged, right? Because P of course is the del operator, IH bar del. So if A does not have any spatial dependence, then I can interchange that. So now my new Hamiltonian with that approximation in the dipole approximation is P squared minus 2Q P dot A plus Q squared A squared plus the terms from before plus Q5 plus Q. Okay. And now I carry out the transformation that I just mentioned here, right? I put that in here, so I'm going to have to find out what happens to P squared, I'm going to have to find out what happens to P dot A and A squared and all of these terms under the action of these terms. Now this term clearly does not depend on H, right? It's just dependent on the transformation that I wrote down here, okay? And so that term is easily carried out, but this term requires a little bit of algebra to carry out, okay? So let me just do one of these terms, or let me just write down one of these factors, which is the factor RP, R dagger, okay? We want to calculate that one, okay? Just that term first, because if you know this term, you'll see that it's easy to do all the other terms, okay? So this term is e to the minus IQ R dot A over H bar times P, which is minus IH bar del times e to the plus IQ R dot A over H bar. Okay? And first, it should be understood that all of this is operating on some psi, some state ket. So we are trying to find out what happens. Okay, so since del is operating now on this term here, we can just calculate its effect. E to the minus IQ R dot A over H bar times when del acts on this term, it's going to pull down. Okay, there's a minus IH bar that's from here, and then that's going to pull down IQ R over H bar. Oh, sorry, IQ A over H bar. Right? And then e to the IQ R dot A over H bar plus the term where these guys are just interchanged because now del is acting on psi, right? There's a product rule for this. Okay. Okay, and that clearly then is simply equivalent to P plus QA acting on this side. Okay? Right? Those will cancel out, and then this term just becomes Q times A, and we have this result. And in the Coulomb gauge, I can neglect this guy also. So that's part of the Coulomb gauge that I mentioned. Okay, at this point, it's pretty straightforward. Substitute, for P squared, then under this operator, R P squared, R dagger, is simply going to be the same as R P R dagger times R dagger, R dagger, right? I just included this term R dagger R, and that is then going to be E plus QA whole squared. Okay. Okay, and that's it pretty much as far as the first part of the Hamiltonian is concerned, because A of course commutes with itself. So the last term in the Hamiltonian, which is this guy, that's just straightforward, it just stays the same. And we've just shown that the first term is written as P plus QA the whole squared, which we can now expand, right? And that is just P squared plus 2Q P dot A again under the same approximation, plus Q squared A squared. And then we have the second term. Okay, so putting all that back together, I'll just write it down. 1 over 2m. I guess the algebra is not too hard, so I'll just write it out. I thought it was going to be a little bit longer to write out, but it's pretty simple. Minus 2QE P plus QA dot A plus Q squared A squared. And plus V of R. So this is the R, H, R prime part. Right here. Okay? And then I still need to calculate the other term, IH bar, dou R over dou T, R dagger. Okay? Which is quite simple. Dou R over dou T is going to just pull down the R dot dou A over dou T times the R dagger. So this term is just IH bar minus IQ by H bar R dot dou A over dou T. And in the Coulomb gauge, which is what we were going to, which I promised, that in the Coulomb gauge we are now going to set E equals minus dou A over dou T at R equal to 0, T. So this is the application of the Coulomb gauge over here. So this then becomes Q E R dot as promised. So minus sign. That's a plus sign, isn't it? Oh, well, there's a minus sign from E. So, several minus signs, but it goes. So there's a minus sign Q R dot E. And Q R is the dipole moment operator. So this is the mu that I wrote down. Okay, so that's the origin of the mu dot E term. And then all the rest of this you can easily convince yourself that that will just work out to P squared over 2m plus V of R. So we are left in the end with this Hamiltonian that we promised. Okay? I should mention that in some textbooks you will see the interaction written this way, which is not gauge invariant. which is that what they'll say is that H, which is the question maybe also related to what Chen Shu had asked, which is suppose you apply the Coulomb gauge right here. Okay? So you expand this, right? So this term is correct, right, so far. And we have already applied the Coulomb gauge by neglecting phi. Okay? So now we have the term minus q p dot a plus q squared over 2m a squared. Okay? Right? Because del dot a equal to 0, we can say that p commutes with it. Right? P commutator A is P dot A minus A dot P, and if del dot A is 0, right, then this commutator will also be 0. So this is the application of the Coulomb gauge right at the Hamiltonian level without making any unitary transformation. And you'll end up then with the Hamiltonian H equals P squared over 2m minus q over m p dot a. And so in some textbooks, you'll see that the interaction between the electromagnetic field and the electron in the Coulomb gauge is written as p dot a. Okay, so the interaction part, right? You're also, of course, be a part of that. I'm telling you that this is wrong. Okay, so but just so you know why it's wrong. The reason is that this Hamiltonian is not gauge invariant, right? Because you have not made any transformation on the state vector psi. You have left it as just the same psi that you had when you started off. Okay? So you didn't take care of all those transformations, which we have done explicitly in this one. Okay? Equivalent. So this will actually lead to differences from the predicted transition rates, for example. For example, if you apply Fermi's golden rule to this Hamiltonian and apply it to, say, transition rates of a hydrogen atom or some other atom, you will actually find a different answer than if you apply mu dot E to it. Okay? So there's a very clear difference between these two Hamiltonians. But there are still textbooks which use this, so just be careful of it. Did that also maybe answer your question about when to apply the Coulomb gauge?
Yeah.
Because the Coulomb gauge in this case is indeed applied, like you said, right away to the Hamiltonian. So we didn't apply that right away in our case, right? Is that clear, the distinction? Here we just apply Coulomb gauge directly. Don't do anything else. Just apply it at the Hamiltonian level. But that would be wrong, because in quantum mechanics, if you want to do it correctly, you have to apply the gauge transformation to the electromagnetic fields and also to the state vector psi, which we effectively did with this unitary transformation that I wrote down earlier, that I just erased, the R. Okay, that was effectively carrying out a gauge transformation on the state vector psi also. Okay. Okay. Let's stop talking about that, because in the end, it's a theoretical sort of treatment, but it's very, I guess it's important to know that at the formal level, everything is correct now. Okay. So what we want to now do is we want to use this Hamiltonian when we consider the interaction of an atom with an electromagnetic field. Because as we know, it's easier in the lab to generate E's and B's and measure them than it is to measure A and phi, which are anyway gauge dependent. And now we have, so if you want to know more, like for example, as I said, you can read section 5.1 and 5.A of Scully, for more. More details. See Scully. This is Scully and Zubairi quantum optics. It has a white cover with a sort of bullseye pattern on the front. Okay, so now I'm going to actually get into the actual treatment of electromagnetic field interacting with an atom. Okay, so atom field interaction. This was just to set the validity of the Hamiltonian, showing that it is indeed valid. And now we are actually going to study the problem. So, and the material system that we'll be considering can be anything as long as it is has two localized electronic states. Okay, say hydrogen atom, 1s and 2p. Those are two localized electronic states, or it could be the states of a quantum dot, right? The conduction and the valence band levels, for example. Those would be two localized states of the quantum dot, or could be a exciton that's bound to a donor in a semiconductor. That also is equivalent to similar to a quantum dot. NV centers, already mentioned, also have these kind of levels. So do transmon qubits in superconductors, they also have these kind of levels. So there are many systems where there'll be like, usually there are multiple levels, but let's just look at two of them to begin with. Okay. So we have a ground state, 1, and some excited state of the electronic, this is the electronic states. So what we are requiring then is localized states. And the reason we require that is because we want the electronic wave function R, or A if you like, of the atom or whatever to be far less than lambda, right? For the dipole approximation to be valid, we don't want the electron to be so far out that it starts to see the variation of the wave functions. Okay. And then we are also assuming this thing here that these ground and excited states are non-degenerate. So there are not more levels here. We'll come to multi-level systems later on, but right now we're just taking two-level system. So we just have two quantum states, 1 and 2, and then we are applying our electromagnetic field E of R, T. Okay. And of course, as we know, we are going to only care about R exactly at R equal to 0 or R equal to R naught, where the atom is located. So this E of R, T, I'm going to write it down. It might have in general some polarization, some slowly varying amplitude, E to the I k dot R minus mu t plus E star R comma t e to the I k dot R minus I e dot k dot R minus. Okay. And our interaction Hamiltonian V or whatever you want to call it is minus dipole moment mu dot E. So let's look at this dipole operator mu and evaluate it in the space of 1 and 2, these two level systems. Okay. So the dipole operator mu is, of course, we can write it as this 1 times mu times 1. We haven't changed anything. And then we use a complete set. This may seem like overkill, but I'll just explain why in a second. Essentially, it's a 2 by 2 matrix, right? But of course, you can expand this to any number of levels. So it's good to have this general sort of idea, right? So it's a 2 by 2 matrix, right? And so we're going to have terms mu 1 1, which is also a vector, remember, because this is a vector operator, times 1 plus, so we have the diagonal terms, and this is how we write the operator, right? We want mu 1 1 times the operator on the state 1, mu 2 2 times the operator on state 2, which projects onto state 1 and 2, plus then we have the off diagonal terms mu 1 2, 1 comma 2, plus mu 2 1, 2 comma 1. So we have 4 terms, right, where mu and m represents the dipole operator in between these states, n and m. Okay. So it's a vector operator in general, because we have not yet said that the electric field has a certain polarization. And in homework 2, you will derive some of these dipole moments using things like the Clebsch-Gordon or Wigner-Eckhart theorem. And I'll give you all that in the homework itself, so the way it should. Just to remind you of how these things are calculated. Because that's of course important when you're actually considering any real system to calculate the interactions. And for spherically symmetric atoms, it's quite easy to show that there's no permanent dipole moment. That is, if the system is in an energy eigenstate 1 or 2, there's no dipole moment for that particular state. Okay? That's true for spherically symmetric atoms, but it may not be true in general for other types of systems. For example, with certain systems like NV centers, the excited state of the NV center, that is the excited orbital state, has some dipole moment which makes it sensitive to electric fields in the vicinity. This is also true for other systems like quantum dots, okay, where the symmetry is broken, or other kinds of excitons, so on. This may not be true in general. Okay, solid state systems obviously do not have the same full symmetry of atoms. Okay? But for spherically symmetric atoms, this is usually true. There are also, of course, molecules. In molecules, this will not be true, right? So that's an easy example. You can almost see that, right? When you have a molecule with like 2 different atoms, for example, then it's obvious that there could be some charge separation even in a state, a ground state or excited orbital state. Okay. Anyway, we are going to assume this just because it makes the Hamiltonian easier. And so, for this system then, hopefully, so one thing I'm going to do, which is depends on the textbook, but we are going to assume H naught, that is the H atom or H naught, which is the Hamiltonian in the absence of any external perturbation, external drive, is purely H bar omega times 2. Okay. Which means I set the 0 of energy at the 1 energy level, at the energy of the ket 1, sometimes you see the zero of energy set in between. Okay, because then it makes it look just like a spin system. And we'll come back to that when we discuss qubits or spin systems in a bit. It's pretty straightforward, I'm sure. You guys will have already seen it probably. Okay? But anyway, so now the full Hamiltonian of the system is h bar omega 2 2 minus mu 1 2 comma 1 2 plus mu 2 1 2 1 dotted with E naught. And now what I've done is in the dipole approximation said that I can ignore any variation of this electric field cross atoms, so set R equal to 0 or R equal to R naught, whatever you want to call it. Maybe R equal to R naught if you like. And then, so I'll write down what these E's are in a second. But essentially we have this term. So this is the Hamiltonian where this E naught of T is simply the full, which might have a phase factor associated with the position of the atom. Obviously if there's just one atom, then just set R naught equal to 0 and you're done. If you have multiple atoms, then you may have to worry about the phase difference from one atom to the next in the presence of this electromagnetic field. Okay? But this is just the slowly varying amplitude evaluated at position R equals R naught, where the atom is located. Okay, pretty straightforward so far. And then, so now we need to solve the equation of motion under this Hamiltonian. And so, of course, let's start with the simplest, right? Which is just use the probability amplitudes for the system. It's a two-level system, so the way the state ket is quite straightforward. So this is the probability amplitude method. Which is that apply psi of t equals some coefficient C1 that varies with time plus C2 that varies with time times state ket 2. Okay? This is the Schrodinger picture. The state vector is evolving with time t, and then of course we apply the Hamiltonian, the Schrodinger equation, which is h psi. So that gives rise to a matrix equation in the 1 and 2 bases. So this is going to have a form which is minus d12 dot e naught e to the minus I nu t plus e naught star e to the plus I nu t, and then h bar omega over here, and then this term here is just the same as that one, except with d21 e naught e to the minus I nu t plus e naught star e to the plus I. Times C1 T we're done, right? So this two-level system, we have the equations of motion, which we can also write out explicitly instead of in matrix form, like. So IH bar C1 dot of t equals minus D12 dot E naught e to the minus I nu t plus E naught star e to the plus I nu t times C2 of t, and IH bar C2 dot of t is equal to H bar omega C2 of t minus D21 dot E naught e to the minus I nu t plus E naught star to the plus I nu times C1. Okay, looks like we are done, right? The problem is over. Unfortunately, these equations are not solvable for arbitrary electric fields. Okay, so even this very simple system, two-level atom with an electromagnetic field, is not solvable analytically, right? I mean, of course, you can numerically integrate these equations. Okay.
Can we just double check that U1Q is the same as the mu1Q, right? It's a
Oh yes, I'm sorry.
Oh.
I always forget. Sometimes in my notes I have D for dipole, sometimes I have mu. Let's fix that. Or how about we agree that you'll understand that it's the dipole moment if I write D, right? Is that okay? Okay. So hopefully, I'm sure you've all seen this and it's not too new. But the problem, as we were mentioning, is that usually in most graduate courses you will stop with these equations and you'll make approximations, right? You'll do first order time-dependent perturbation theory, for example, or maybe second order, whatever you've seen in your courses. But if you want to actually solve this for any arbitrary electric field, arbitrary strength, arbitrary time, whatever, it's not possible. Okay? So we have to make some approximations. And so we will assume, first of all, that things are not crazy. And we will start with some simpler situations where we can indeed obtain analytical solutions. So, for example, we know that typically with the strengths of electromagnetic fields that we can apply to the system and the magnitudes of the dipole moment, typically we know that D12 times E naught, the magnitude of this variable, right, the strength of the dipole times the electromagnetic field strength, is typically going to be much smaller, or divided by h bar if you like, to get it into a frequency unit, is typically going to be smaller than both omega or nu. Omega, of course, is the separation between the atomic energy levels, and nu is the frequency of the drive field, right? Typically these guys are going to be much bigger than the strength of the field that we can apply, because this part is proportional to the dipole moment times the strength of the field. Okay, so what we're going to do is going to simplify the equations, and first of all we're going to get rid of this dependence on the field frequency that's in the equations of motion. So this nu, which is over here, this term is rapidly oscillating at the frequency of the field, right? And so that's kind of silly to work in that reference frame where that thing is rapidly oscillating and it's just a simple harmonic dependence in this case. So let's get rid of that and try to go to a more slowly varying frame. Okay, and the slowly varying frame has a name which is called the rotating frame. Okay, So what I'm trying to say is that, or physically speaking, that C2 of t, for example, is going to oscillate with a frequency comparable to the optical frequency or the driving frequency. But that's not interesting to us, okay? So let's just try to focus on the evolution by defining this new slowly varying amplitude. So I'm going to call, in this system, let C1 of t is going to go to a new set of variables, C1 tilde of t, and C2 of t is going to transform to a new variable, C2 tilde of t e to the minus I mu t. Okay? So we've taken out this fast oscillation e to the I nu t with this new variables. So we're going to solve for the equations, rewrite the equations of motion in this new set of variables. Clearly, the most, the thing we need to know is what is C2 dot, and that's pretty straightforward. That's going to be C2 tilde dot e to the minus I nu t minus I nu C2 tilde e to the minus I. Right? Straightforward product rule. Okay, then the first equation, IH bar C1 tilde of t is equal to minus D12 or mu12 right? It's still the same from there. Times our C2 of t, which now goes as C2 tilde of t times e to the minus I mu t. Okay? And so this guy, in terms of C1 tilde dot of t, and of course, C1 dot of t is equal to C1 tilde dot because there's no time dependence. Okay? This first equation then, C1 tilde dot is equal to I mu12 over h bar. And now what I've done is basically, I'll keep the dot if you like, a little longer. So we see that we get one term in this interaction which goes as E naught star of t, and the other term goes as E naught of t at twice the frequency. Okay? And this will of course help us to make a simplification very soon. That's the first equation. Okay, you can easily do the second one. I won't go through the details. The second one is basically C2 tilde dot is equal to I times nu minus omega C2 tilde plus I d to 1 mu to 1 over h bar divided with E naught t plus E naught star t e to the 2I nu t times C1 tilde. Okay? So we have two sets of equations, and now we see that all of the sort of the fast part of the fast oscillations have gone into these terms over here. Okay? This is the transformation to the rotating frame. So this is called the rotating frame. And it's also equivalent, as you'll see in a little bit, equivalent to an interaction picture. Okay. But the interaction picture is different from earlier because now the interaction picture is basically one in which we have gone to a term that will, that is sort of, if you like, with the electromagnetic field. And it's a little harder to see because in this sense, the electromagnetic field has no Hamiltonian, right? Remember, the electromagnetic term is purely coming in the interaction. There's no term for the electromagnetic field itself. The reason is the electromagnetic field, we took it as classical, okay? So the electromagnetic field is classical, which means that any interaction with the atom does not change the electromagnetic field, does not change its energy, does not change its amplitude, and therefore we don't even have it in the Hamiltonian. And that's why it makes it a little harder to see that there's an interaction picture. When we do the quantized version, it will be much more obvious that this is indeed an interaction picture by going to this rotating frame. Okay? But I will not get into that right now. We'll deal with that when we actually see the quantized version of this Hamiltonian. Okay, pretty simple, I hope, right, so far? And now we want to make one more approximation, which is also has an important name, which is called the rotating wave approximation. And to do that, I'll formally integrate equation 2, okay, over some time duration. And we'll see this again later on when we do adiabatic elimination as well. But let's just do it now to show you the important approximation which we're going to make. So I'm going to take this term, and this guy here, nu minus omega, is usually given a symbol delta, which represents the detuning between the driving field nu and the atomic frequency omega. Okay? So delta is the detuning, which is the difference between these two fields. Okay? Alright, so now formally integrate the equation 2 over some time delta t. Okay? So integral 0 to 2 delta t c2 dot. Okay, and I'm dropping the tildes now, hopefully it's not a problem. You remember that this is all in the rotating frame. Okay? Let's put the tilde down, since I have it on one side and not the other. Okay. We're going to assume that this delta t is small, but essentially what I'm trying to say is that it's large enough that we can make the approximation that everything is smoothly varying, but small enough that we don't have to worry about the total development of the field over the entire time. So what I mean by this is, okay, let's just integrate this, right? So I get C2 tilde at delta t minus C2 tilde of 0. And what I'm assuming is that the time is so slow or is so small that C2 tilde and C1 tilde have not changed much. They are pretty close to their values at time 0. But we are looking at this change approximately, which is, and you'll see this in just a minute, C2 tilde of 0 times delta t. So that's the approximation. So C2 tilde of t has not changed much over this time interval delta t. Okay? So I don't have to worry about what it happens from time 0 up to time delta t over here. Okay? So, plus, then I have, so basically we are assume that nu is far greater than 1 over delta t, and nu is also far greater than delta, or this value d21 times E naught over h bar, mu, sorry. So nu is the biggest frequency in the problem. That is sort of our approximation here. Okay? And everything else is slowly varying on this time scale delta t. So delta t is large enough that there are many, many oscillations of this nu or of this term e to the 2I nu t. Okay? But there are lots of oscillations of that term, but all the other guys are effectively almost constant. Almost. Okay? So just as I said, this is just to explain to you where this approximation comes from. So then this term over here can be evaluated at time 0, right? Divided by h bar times again delta t plus, now this term though, right, I'm going to have to worry about it because it has some variation over the time scale delta t. So I have to keep it in mind. So I cannot neglect its variation. So I integrate just that term, okay, e to the 2I nu t. So I get e to the 2I nu delta t over 2I nu, and then I've also set C1 tilde equal to 0, or at time t equal to 0. So basically what I'm saying is everything remains roughly constant, but I have to worry about the variation of this guy from time 0 up to time delta t. And there may be a factor of -1 here as well, so, because I'm integrating only that term. Is that clear? There's a formal integration under the approximation that delta t is slowly varying compared, or delta t is small compared to the variations in C2 and C1 and E, but it is or 1 over delta t, the frequency is much, much smaller than the frequency nu. Okay.
I'm sorry,
Yes.
confused. Why you can see like around the time delta t, the C1 and C2 is basically the same. I mean, why is the C2 delta t close?
It is close to. Okay.
Oh,
Imagine some. Okay, so we know that because of the presence of the electromagnetic field, E naught, C1 and C2 will vary a little bit. We're choosing some time scale. Imagine, think about it like perturbation theory.
Okay.
We're choosing some time scale delta t where they have not varied significantly over that time. So we can roughly approximate inside these integrals that C2 of tilde is almost the same as at C2 of tilde at 0. This is a first order approximation.
Okay.
Think of it as a first order. Okay? The only term that I claim is going to be important is this term. Okay? Because that's the only fast oscillating term on this time scale delta t. But as you can see, that term has a 1 over 2 nu in it. Okay? This 1 over 2 nu, where nu is very, very large, means this term is effectively 0. If you want to be more careful, we can actually work out all the corrections to this. Okay? And in fact, I could assign that as a homework problem. Okay? It's not very hard, right? I mean, you just start approximately, you take the first order and put it back in, and then expand to the second order, right? And you will see all the corrections come up. And we'll do some form of this very soon. Okay, and so this term here is called the counter rotating term. Because it oscillates at a frequency 2 times the actual frequency of the electromagnetic field. So this term we're going to set equal to 0 in this approximation. We're only allowed to do this, as you can see, if these terms are small, right? Mu, what you'll see in a minute, that this is called the Rabi frequency, mu times E divided by h bar, right? This is the Rabi frequency, which you'll see in just a second, or you might have already seen before. So that term we're assuming is small, okay, as we show it here. We're assuming delta is small, okay, that's also here. Okay, we're assuming the time scale delta t is large compared to the time period of, or the oscillation period of the electromagnetic field. So nu is the largest frequency in the problem. Okay? Or equivalently, you could say the detuning between nu and omega is small. Okay? Nu and omega are very close to each other, and that nu is therefore much greater than delta or the Rabi frequency, the detuning. So detuning and Rabi frequency are small in comparison to the actual atomic frequency or the drive frequency of the electromagnetic field. We'll also implicitly assume that E also does not vary very fast. So that's another thing. So we have also assumed that E is a slowly varying amplitude, because otherwise we would have to have corrections to E naught which are involving dE over dt, right? That is the variation of the electromagnetic field over this time scale delta t. We are assuming that also is small implicitly, because we didn't have to worry about any of these when we went from this step to this step. When we formally integrate, we went from here to here. So we have effectively assumed that all of these guys are constants on this time scale, and we are neglecting all of their first order variations. So it's very straightforward now to simply take this, put it back in, and get the second order, right? I mean, that's just standard perturbation theory type argument. So the point of all this is we have neglected this term, and by neglecting this term, this is called the counter-rotating term, we are only left with this term over here. And so you can see we have simplified the effective equations of motion for the system. So these were the original equations of motion, and now, since we have shown that we can neglect this this term over here, these terms effectively we have set to 0. Okay, in the rotating wave approximation. So this is the rotating wave approximation. We often refer to as RWA. Okay? So in this rotating wave approximation, if the dynamics of C2 tilde and C1 tilde are slow, okay, then these terms which go as e to the 2i nu t can be neglected, and I've shown you specifically why that's true. It's because when you formally integrate the equations, this term will always be accompanied by a denominator which goes as 1 over 2 times the frequency. And so it's going to, when nu is very, very large, that term is going to be small. So obviously you can destroy or go beyond the approximation if, for example, nu is small, right? If nu is actually small, as might happen in some systems, relative to, say, the detuning or to the amplitude of the magnetic field, the electromagnetic field, that is the Rabi frequency, if it's large, and the frequency nu is maybe comparable to that, right? In the comparison, you can actually do a numerical solution for these, which shows you when this starts to break down. Okay? And typical range is somewhere between 5 to 10%. When the Rabi frequency, which is usually the one that you vary a lot, right? You can vary the amplitude of your electromagnetic field, right? You can vary the Rabi frequency, and that gives you a knob, and if you turn it up to about 5 to 10% of the actual frequency, the transition frequency, you start to see changes from the actual approximation, this rotating wave approximation that we're making. But as long as it's much less than that, then you're good. Okay? And it's very easy to be much less than that in the optical frequency regime. Right? When you're in optical frequencies, nu is on the order of 100 terahertz, right? For optical systems, say excitons or plasmons or some other system, polaritons, and so on, NV centers, etc. This is usually a very good approximation because it's very hard to turn up the amplitude of your electric field for example, of the laser or something to achieve, because the dipole moment of an atom is quite small, right? An atom, if you think about it, it has a typical dimension of angstrom, right? And so E times the angstrom, that's quite small, right? The dipole moment. So your electric field would have to be enormous to start approaching 100 terahertz frequencies, or even 1 terahertz, say, frequency, right? 1 terahertz Rabi frequency is quite hard to achieve for even a laser, unless you have some very special laser system. Okay? Alright, but in this rotating wave approximation now, we have, so rewriting these equations of motion, then C1 tilde dot of t, and now I'm going to define the Rabi frequency that I just promised you. I'm going to say that there's a Rabi frequency, which I'll just write down in a second, which goes as this. I'll just write the equation of motion and define the Rabi frequency in a second. And C2 tilde dot of t is I delta C2 tilde of t plus I omega t over 2 times C1 tilde of t, where now omega, the Rabi frequency, omega is defined as 2 times mu to 1 dot E naught over A. This factor of 2 is a little bit always an issue, okay? It comes about in different places. Like in some books or something, you will see it without the factor of 2 written down. Okay? In which case, you can neglect this factor of 2 over here in this system. Okay? So just the convention that people use can be different. So, but the final equation of motion always has to look like this, right? And the reason for that is we chose that if you add these two together, for example, this will go as 2 times cosine nu t, right? So there will always be a factor of 2 somewhere. Unless you were very clever and at the beginning had put a E naught divided by 2 here very carefully. If you chose to do that, of course, then you will not have this problem. But then the Rabi frequency will automatically have a definition of 1/2 inside it, put in from the amplitude E naught. But in my definition, this is what I'm using. And it's possible that somewhere along the way, I'll make a mistake and drop the 2. So you should watch out for those factors. I do not promise to be perfect to up to factors of 2 and stuff. You always have to look at your equations of motion again to make sure that you took care of those factors of 2. Okay, so that then in the rotating frame and the RWA, rotating wave approximation, is the new equations of motion for the 2-level atom. So we're almost out of time. So let's just talk about what is going to happen. So these equations can be solved analytically for constant field strength, for different types of systems, etc. And we will look at those examples. For example, under resonant excitation, off resonant excitation, we look at rest states and adiabatic elimination and all that thing very quickly in the next class. These are the equations of motion that you're most likely going to see or think about when you consider a 2-level atom which is being resonantly excited or close to resonantly excited by an electromagnetic field. So these are the equations of motion, and you can see that to get to them we had to apply 2 approximations: rotating frame, or we went into a rotating frame and we applied a rotating wave approximation. Okay?
So I understand, like you said rotating frame, we just put it into another frame.
Yes.
Why would do any approximation there?
We didn't do any approximation in the rotating frame.
Okay, so
But when we went from I just erased it, but those were the actual equations of motion. They had an e to the 2I nu t in it.
actually that's the approximation.
That's the approximation. I neglect the e to the 2I nu t because I know in any integration of the motions, that correction, the fact that e goes as e to the 2I nu t, that term is there. in the Hamiltonian. It's always going to be there. You can think about it as when I move to the frame, there is a term that is near resonant, which is at DC effectively now in this new frame, right? Because I've got, let's imagine I was at near detuning or zero detuning, right? Then effectively what I said is there is a DC component to my electromagnetic field, and then there is a term or a frequency of the electromagnetic field that is at 2 times the optical frequency or the electromagnetic field. So if I look at the frequency spectrum after moving to this rotating frame, there's one which is at DC in this rotating frame, and there's one that's at 2 times the optical frequency or the electromagnetic frequency. Now if the electromagnetic frequency is very large, this other term will have almost no impact on the dynamic. If it is small, then it has some impact. Okay? And it's proportional to the amplitude. That's why if the amplitude is very large, then also it can have some impact. Okay. Alright, I think we're done for today, and in the next class we'll finish up this discussion of 2-level atom dynamics. Yes. That's right, because the electromagnetic field has some high frequency. Get rid of those fringes and just look at the envelope. Exactly. Right.